Today I would like to present on the topic Introduction to Fractal Geometry and its application in real world. We know geometry is a branch of mathematics which is concerned with points, lines, curves and surfaces. In mathematics, a fractal is a non-regular geometric shape that has same degree of non-regularity on all scales. Fractals can be thought of as never-ending patterns. It is a complex picture created using iteration and single formula. The other important point is fractals are small matters that resembles the whole. That is, they are infinitely complex patterns that are self-similar across different scales. They are created by repeating a simple process over and over in an ongoing feedback loop. Geometry which is able to describe the shapes of irregular and fragmented patterns is known as fractal geometry. Examples are everywhere in the forest. Trees are natural fractals. Also, we have the idea that there is no perfect shape for mountain as well as clouds. So in that case, we make use of fractals. So we can draw the natural object with the help of fractal geometry. The other examples of fractals are snowflakes, lightning and ferns. These are some of the examples of fractal geometry. Benoit B. Mandelbrot is the father of fractal geometry. In 20th century, Mandelbrot introduced fractal geometry. He referred to himself as a fractalist and is recognized for his contribution to the field of fractal geometry, which included coining the word fractal as well as developing a theory of roughness and self-similarity in nature. He says, clouds are not sphere, mountains are not cones, coastlines are not circle, and bark is not smooth, nor does lighting travels in a straight line. Now we can discuss the properties of fractal geometry. First one is self-similarity. If we have two squares look like each other, it is similar. But if we have a big square inside it in a small one, it is self-similar. We can magnify many times and after every step we can see the same image. This is a property known as self-similarity of fractal geometry. The other property is non-integer dimension. Many natural phenomena are better described using a dimension between two whole numbers. We know dimension of a straight line is 1 and dimension of a square is 2. But the dimension of a fractal curve is between 1 and 2. Example is lightning. Dimension of a lightning is neither 1 nor 2. It is in between 1 and 2. The other example is a folded or crushed paper. We know the dimension of a original paper is 2. But if we fold it or crushed it, the dimension of that paper is neither 2 nor 3. It is in between 2 and 3. So, fractals have non-integer property. Next is Mandelbrot set. Mandelbrot was one of the first to use computer graphics to create and display fractal geometric images, leading to his discovery of Mandelbrot set. On 1st March 1980, Benoit B. Mandelbrot discovered the Mandelbrot set. During his research at IBM, he came across a structure with self-similarity at all scales, that is fractal. The term Mandelbrot set is used to refer both to a general class of fractal set and to a particular instance of such a set. The boundary of a Mandelbrot set contains infinitely many copies of Mandelbrot set. In fact, as close as we look to any boundary point, we will find infinitely many little Mandelbrot. Equation of Mandelbrot set is Z is equal to Z square plus Ci. When Mandelbrot equation is given to a number representing a point and that number is repeated through the equation, this is called iteration. Mandelbrot sets generated by iteration. Iteration means repeat a process over and over again. Using iterated values of Mandelbrot set, Benoit B. Mandelbrot created a picture. This black region represents a Mandelbrot set. However, the Mandelbrot set is a famous fractal of all. It's not easy to describe it visually. It looks like a man, a cat, a cactus, or a cockroach. It has little bits and pieces that remind us of at most anything we can see out in the real world, particularly living things. There is indeed an infinite variety in the Mandelbrot set, just indeed as there is an word of nature. We see shapes that remind us of elephant trunks, tentacles of octopus, seahorses, and compound insect eyes. There is certainly some connection between Mandelbrot set and the way nature operates. The Fractal Geometry of Nature was published in 1982. When Benoit was exploring this set, he never felt that he had invented it. He never felt that his imagination was rich enough to invent all those extraordinary things. He knew he was making a discovery. Nature often finds the same solution to many different problems, like how to drain water from the land into the oceans and how to get blood from our hearts to our fingertips and back again. And the templates that nature uses are fractals. Fractal geometry is the language of nature, of familiar and apparently random forms like trees, coastal lines, rivers, lightning, and human body, a winding coastline, the branching structure of fern, spacing of stars in the night sky, etc. With fractal geometry, the Benoit Mandelbrot has given us a new language which is applicable throughout all the sciences and is one which has a mind opening effect and on most people who come across it. This new language is changing our lives and the world of scientific endeavor. The another variant of Mandelbrot set is Buddha Brot. The fractals look like a bloating Buddha. Buddha Brot is probability distribution over the trajectories of points and escape the Mandelbrot fractal. Its name reflects to classical depiction of Gautama Buddha seated in a meditation pose with a forehead mark called Tika and a traditional top knot. It was first posted by Melinda Green in 1993. The fractals is rendered by splitting the canvas into a matrix where each element in the matrix represents the iteration. Now we can have a look on Sierpinski triangle. It is a fractal attractive fixed set with the overall shape of an equilateral triangle subdivided recursively into smaller equilateral triangles. In 1915, the Polish mathematician Wacław Sierpinski formulated an equilateral triangle fractal by connecting smaller equilateral triangles. The Sierpinski triangle activity illustrates the fundamental principles and fractals, that is, how a pattern can repeat again and again at different scales, and how this complex shape can be formed by simple repetition. The Sierpinski triangle is self-similar fractal. In this case, the repeated procedure is removing the triangle created by connecting the midparts of the sides of the previous triangle. This leaves us with three Sierpinski triangles, each of which has dimension exactly one half of the dimensions of the original triangle and area exactly one fourth of the original area. Also, each remaining triangle is similar to the original triangle. The Sierpinski triangle is an example of geometric representation of geometric sequence. There are three steps to make Sierpinski triangle. The first step is start with an equilateral triangle and locate the midpoints of each of the sides of triangle. In the second step, connect each of the midpoints with a line segment and remove the triangle you just created. In the third step, you now have three equilateral triangles within the original equilateral triangle. Repeat the first two steps for each of these triangles. This process can be continued indefinitely or until you choose to stop. Now we can count the area of the white triangles. Let us take this as an infinite geometry sequence. In our first cut, x by 4 is removed, where x is the original triangle's area. This is indicated by the second triangle in the picture. In our second cut, 3x by 16 is removed, as indicated by the third triangle. This pattern continues infinitely and the sequence will be x by 4, 3x by 16, 9x by 64, 27x by 256, etc. In order to find the total amount of white space, we have to add all these terms. The first term is x by 4 and the ratio is 3 by 4. We now use the formula for geometric infinite series, a1 by 1 minus r. a1 is the first term which is equal to x by 4. R is the common ratio which is equal to 3 by 4. We have total white areas equals to x by 4 by 1 minus 3 by 4 which is equal to x. For integer number of dimension d, when doubling a side of an object, 2 raised to d copies of itself are created. That is 2 copies for 1 dimensional object, 4 copies for 2 dimensional object and 8 copies for 3 dimensional object. For Sierpinski triangle, doubling its sides creates copies of itself. Copies is equal to scale raised to dimension. 3 is equal to 2 raised to d. Adding logarithm to both sides, we will get log 3 is equal to log 2 raised to d. Log 3 is equal to d log 2. So we can find the value of d, which is equal to log 3 by log 2. That is, d is approximately equal to 1.532. Thus, we can find the dimension of Sierpinski triangle using the scaling dimension relation. Now we can see what is fractal antenna. Fractal antenna is an antenna that uses a fractal to maximize the effective length of the material within a given total surface area. Their advantages are good multi-band performance, wide bandwidth and small area. The gain with small size result from constructive interference with multiple current maxima afforded by electrically long structure in the small area. The Sierpinski triangle with similarity dimension about 1.58 is commonly used by researchers to study fractal antennas. Some researchers have disputed that fractal antennas have superior performance and fractal antennas allows phone to process the transmission of a wider range of electromagnetic frequencies and reduce the total number of antenna required. Dr. Nathan Cohen experimented fractal antenna to fulfill 2 wishes: to make an antenna as small as possible and to make an antenna cover many bands. Fractal antennas have space-filling properties that can be used to miniature classic antenna elements and overcome some of the limitations of small antennas. Many fractal elements antennas uses the fractal structures as a virtual combination of capacitors and inductors. Math language of fractals. IFS. IFS means iterated function system. IFS is a method of generating fractals. Consider X is an Euclidean space and the mapping R all translate linear transformation. Based on series of affine transformation, W of xy is equal to ax plus by plus e and cx plus dy plus f, where a, b, c, d, e, f are responsible for the moment of fractals. Consider W1, W2, W3, etc. Wn as a set of affine linear transformation. Let S be the initial geometry. W of S is equal to union I equal to 1 to n Wi of S, where W is known as Hutchinson operator. Koch snowflake. The Koch snowflake is a fractal curve and one of the earliest fractals to have been described. The Koch snowflake can be built iteratively in a sequence of stages. It is also known as Koch curve, Koch star and Koch island. Snowflake is used to show that it is possible to have figures and are continuous everywhere but differentiable nowhere. A Koch curve is a fractal curve that can be constructed by taking a straight line segment and replacing it with a pattern of multiple line segments. Then the line segment in that pattern are replaced by the same pattern. The Koch snowflake is self-replicating with 6 smaller copies surrounded one larger copy at the center. The first stage is an equilateral triangle and each successive stage is formed from adding outward bends to each side of the previous stage. making smaller equilateral triangle. The areas enclosed by successive stages is in the construction of the snowflake coverage to 8 by 5 times the area of the original triangle. The perimeter of the coach snowflake in the successive stage increases without a bound. That is, snowflake encloses a finite area but has an infinite perimeter. The number of sides n. Na is equal to 3 star f raised to a in the eighth iteration. For each iteration 0, 1, 2, 3, the number of slides are 3, 12, 48 and 192 respectively. And the length of a side is found out by the formula SA is equal to S by 3 raised to a. And perimeter can be found out by 3 PA is equal to NA into SA, which is equal to 3 into S into 4 by 3A for the 8th iteration. Now we can look how fractal geometry help in detection of cancer. When an immortal cells of our body are transformed into cancerous, only at this particular stage fractal geometry is found on the cell. Early detection of cancer is crucial to treatments. Cancer cells typically display abnormalities including unregulated cell growth. Fractal analysis can be used to analyze regularly shapes, figures and measure morphological complexity. Changes in the fractal dimension between cancer cells and healthy cells were analyzed and compared. Results shows that fractals can detect cancer cells. It has great potential for yielding insight into the morphological characterization of tumor growth. Fractal geometry is used for describing the pathological architecture of tumors and may serve as an indicator for cancer detection and cancer treatment effectively. Using fractal geometry, GeoSmart's team is able to identify cancer cells more relatable and more faster. The emergence of fractal geometry in the programming towards cancer was shown only for human cervical epithelial cells. Now we can look how fractal geometry affects in climate change. There are many phenomena based on fractal geometry in nature. Climate change is also an application of fractal geometry. If an essential structure in nature is identified and the principles of fractal geometry are applied to decompose it, predictions about how the structure will act in the future can be made because fractals adhere to the mathematical principle of self-similarity. The Earth's climate system is characterized by complex interactions between the atmosphere, oceans, ice sheets, land masses, and the biosphere. Astronomical factors also play a role in relationship to the great changes like the shift between ice ages. This new characteristic of the climate will make it easier for climate research to differentiate between natural and human-induced climate changes because it can be expected that human-induced climate changes will not behave in the same way as natural fluctuations. Predicting the size, location, and timing of natural hazards is virtually impossible. But now, Earth scientists are able to forecast floods, earthquakes, volcanic eruptions, wildfires, and landslides using fractals. With the help of fractal geometry, Earth scientists are taking Mandelbrot's fractals, approaching one step further, and are measuring past events and making probability forecasts about the size, location, and timing of future natural disasters. In the past, Earth scientists have relied on statistical method to forecast natural hazard events. But when they started using fractals, they found that these patterns contain a level of information that has never been seen using statistical method. It was discovered by comparing the fractal formulas of the size and frequency of hurricanes, wind speed to the historic record of information about past hurricane landfall, location, and timing when we are able to predict the approximate wind speed of the hurricane. When it made landfall, at a given coastal location along the United States Atlantic and Gulf of Mexico coast. Forecasts of hazardous natural phenomena based on the application of fractals are now available to government agencies responsible for planning and responding to natural disaster such as Federal Emergency Management Association and other emergency personnel to be able to better forecast the size, location and time of future events. We can better forecast the probability of a future event. Thanks to Dr. Mandelbrot and earth scientists who have found a powerful new tool to predict future chaotic events of nature. Now we can have a look on Barnsley's fern and fractal geometry. We can see fractal geometry in Barnsley fern. The fern is one of the basic examples of fractals. Fractals are infinitely complex patterns that are self-similar across different scales and are created by repeating a simple process over and over in a loop. The Barnsley fern shows how graphically beautiful structures can be built from repetitive uses of mathematical formula. Modeling plant structures and other phenomena in science was a specialty of Barnsley. In fact, he is said to have inspired many graphic artists attempting to imitate nature with mathematical models. The fern code developed by Barnsley is an example of iterated function system used to create a fractal. Fractals generate points to plot on graph that are the result of iterated calculations. The answer from one calculation is used in the input value to next calculation. One starts with shape plotted on a graph and then the shapes are iterated through a calculation process that transforms them into other shapes on graphs. Starting with 4 shapes, one of which is squashed into line segment. Eventually, a pattern emerges that bears a starting resemblance to a fern. The longer the iteration process, the more intricate the tiny details in the pattern becomes. The complexity of creating the Barnsley fern model, together with the fact that the number of iterations required could be tens of thousands, make it extremely arduous to plot by hand. While it is not impossible, it is much easier and often preferred to use a computer instead. The fern is certainly one of the best examples for understanding fractal geometry. A small part of the figure, when enlarged, reproduces the original figure. An object which possesses this property is called a fractal. From a mathematical point of view, the repetition of patterns at smaller and smaller scales can be continued to infinity. In the real world, nevertheless, the repetition stops after a certain number of jumps. A fractal construction is extremely interesting for reason of effectiveness. For example, if one wants to insert the largest sheet possible in the smallest possible volume by folding it up in such a way that its faces never touch, one must give it in a fractal shape. In addition, the instructions for such a folding are very simple, since it suffices to state that the same folding pattern is repeated many times in succession. This is surely why one finds many fractal objects in nature. The instructions for their growth can be encoded in very little spaces in DNA. Even if in certain cases the scale invariance is only statistical, it is nevertheless rigorously defined with what is called fractal dimension, which measures in a way the degree of roughness of the fluctuations or the boundaries of the object. Now, as a conclusion, I would like to refer all which we have discussed earlier. A fractal is simply a never-ending pattern. Fractals are infinitely complex patterns that are self-similar across different scales. They are created by repeating a simple process over and over in an ongoing feedback. Fractal mathematics has many practical uses, for example, in producing stunning and realistic computer graphics, in computer and realistic computer compression system, in the architecture of network that makes up the internet, etc. Fractals does not exist in real life. They are actually only mathematical models. In real world, we can only apply them as an approximation to real objects. Fractal geometry has become very useful in the understanding of many phenomena in various fields such as astrophysics, economy, or agriculture, and recently in medicine. We can say that we are fractal. Our lungs, our circulatory system, our brains are like trees. They are fractal structures. Fractal geometry allows bounded curves of infinite length and closed surfaces with infinite area. Fractal is a specialized energy storage and renewable energy consulting and engineering firm that provides expert evaluations, technical design, financial analysis, and independent engineering of energy storage and hybrid projects. Fractal geometry has been applied in many exchangers devices including the heat sink, fuel cells, micro reactor, distributor, collector, etc. The Mandelbrot set is the most famous fractal. Far beyond the scope of human eyesight, the natural world is filled with these replicating patterns. It's a fractal world and we are all just living in it. A fractal is a never-ending pattern that repeats itself at different scales. The property of never-ending repetition is called a self-similarity. Fractals are said to be infinitely complex, meaning you can zoom into a photo of a fractal infinitely and you will still find the same shapes over and over forever. Many scientists have found that fractal geometry is a powerful tool for uncovering secrets from a wide variety of systems and solving important problems in applied science. The list of non-physical fractal systems is long and growing rapidly. We have discussed earlier about the Mandelbrot set, which is the particular set of complex numbers which has a highly convoluted fractal boundary when plotted. It is followed by Sierpinski triangle, which is a fixed set with overall shape of an equilateral triangle. Also, we have discussed about fractal antenna known as self-similar design to maximize length or increase the perimeter of a material that can receive or transmit electromagnetic radiation in a given particular area. Then we look up to the basic role of fractal geometry in detection of cancer and climate change. And after we studied about one of the earliest fractal that described about known as Coach Snowflake and also analyzed about the fractal geometry in Barnsley leaf. Fractal geometry provides a way to understand complexity in system as well as just in shapes. We can observe that fractals improved our precision in describing and classifying random or organic objects. But maybe they are not perfect. Maybe they are just closer to our natural world, not the same as it. Some scientists still believe that true randomness does exist and no mathematical equation will ever describe it perfectly. Anyway, I am concluding my words by pointing out that there are still more to explore in fractal geometry and hope they will soon be out. Thank you.